Good evening, everyone. A warm welcome to all the distinguished speakers, faculty members, and participants joining us on the second day of AICTE ATL sponsored faculty development program on quantum algorithms and cryptography, organized by the Department of CSE, AI and ML, KMIT, Hyderabad. Yesterday, we had insightful sessions that laid a strong foundation on the basics of quantum algorithms. Today, we continue our journey with two other enriching technical talks. We now begin the first session of the day, and it gives me great pleasure to introduce Ms. Priyanka, who will be giving the introduction to our esteemed speaker for the first session. Hand over to you, Priyanka.
Good evening, everyone. I'm honored to introduce our distinguished speaker for today's faculty development program, Dr. Vishnu Yarlagadda. Dr. Vishnu Yarlagadda is working at Manipal Institute of Technology, Bangalore, as an associate professor in the School of Computer Engineering since August 2023. Manipal is recognized with the status Institute of Eminence by Government of India, procured NARF ranking 6, and in the band of 601 to 800 based on the recent statistics received from Times Higher Education. Prior to that, he worked at various positions in WIT Vellore, NITK Surathkal, Geetham University, ANTS, and Gudlavaleru Engineering College. He received his PhD from NITK Surathkal in 2019 as a full-time candidate, Masters from Geetham University, and bachelor's degree from Gudlavaleru Engineering College. He did his PhD under the supervision of Dr. Shashidhar G. Kulagudi, Professor CSC in the field of music signal processing. He published around 55 articles in various reputed journals and conferences with H index of 10. One of his articles is published in ACM Computing Surveys, which is ranked A star and procured third rank among all computer science journals, with an impact factor of 16. In addition, he has one article in Elsevier Expert Systems with applications with an impact factor of 7. All of his conferences and articles are indexed in Scopus, and a majority of them are flagship conferences with a series greater than 20. Moreover, he published two patents and edited one book on malware analysis. He has delivered more than 25 guest lectures on IoT, speech signal processing, medical imaging, machine learning, and career guidance talks. He received Best Teacher Award for his excellence in teaching and chosen this profession with passion and working towards it. Today, he'll be sharing his insights on quantum key distributions, which will undoubtedly add great value to our learning and discussions. Let us all join together in extending a warm welcome to Dr. Vishnu Yarlagadda Garu.
Thank you, Priyanka. We are honored to have with us Dr. Vishnu Srinivasa Garu from Manipal University, who will now take us through his expert session on quantum QA distribution. Over to you, sir.
So thank you so much, ma'am, for your detailed uh, profile, that means profile explanation about me. And first of all, I would like to thank to Kishore sir for giving this opportunity and to the management of KMIT. So for giving a chance to deliver a session on quantum key distribution, which is a part of 6-day FDP on quantum computing. And so thank you so much, sir.
Welcome, sir. Okay, continue.
Yeah, and Kishore sir, I came to know that Kishore sir was my super
Uh,
senior in our BTech degree college. Thank you
yes,
so
sir.
much, sir.
Okay, sir. Thank.
And thanks to the management of KMIT as well. Uh, sir, is the screen is visible?
Yes, sir. Visible.
Can I start the session, sir?
Yes, sir. Start.
So basically, I will explain on the whiteboard because it's mathematical. Mathematical. Since I would like to explain with that means one example. So first of all, I'll give the introduction to the quantum key distribution, and
Okay.
slowly I'll take you people from classic cryptography, how that means what is classic cryptography and what are the different types of cryptographic techniques that we had previously. And one second, let me hide it if possible. and panel. Yeah, fine. That's fine. So yeah. So starting from what is symmetric encryption, what is asymmetric? Just I'll take a few minutes, that is around 15 to 20 minutes on those topics, and including RSA. I'll try to cover all those topics in first 20 minutes because I don't want to take much time on them because everyone knows about them. So then I'll take the example how quantum key distribution will work apart from those RSA and all those things, and how it is advantageous. So we shall see one protocol called as BB84. Though there are other protocols, so we shall focus on the BB84 protocol. So in this particular session, so starting with a simple program. Yeah, thanks. So let me start with my explanation. First of all, I'd like to thank my supervisor, Dr. Shashida Kulagodi, for guiding me during my PhD career. So he had taught all those things, and after that, I worked with VIT Vellore, and presently I'm working as associate professor at Manipal. So which is a beautiful campus. These are some photographs of Manipal, how it is expanding in Bangalore region. So this is our MIT, which is a part of Mahe. So these are the first two photos are taken from my cabin itself, and we had one Apple lab, and recently we have collaborated with Decibels and Varia. We have started autonomous mobility as well, providing the security to autonomous mobility. So we had taken one autonomous buggy, and we are trying to enroute the map from one place to another place automatically. The vehicle.
Sir, I don't know do with
Sir, your voice is not audible, sir.
Now it's fine, right, sir?
Okay, okay, now fine.
Someone has unmuted me, I think. Yeah,
Okay,
sorry.
okay.
Now it's fine, right, sir?
I made
Yeah, fine. So we have one. This is Marina Sports Complex in Manipal. So this is about Manipal campus. Since we had to price our institute where we are working always. So coming to the presentation outline. So introduction to cryptography, symmetric public key cryptography, impact of quantum computing and RSA. So someone is muting.
Okay,
Kindly
continue,
check
sir.
it,
Okay,
please. Because I have logged in two devices. One will. Is it fine, sir?
okay, fine, fine.
sir.
Uh,
I will
uh,
go
one
the
coding example also I'll explain with this example.
1 minute, sir. 1 minute. I
Take
want
this. Sir, someone is speaking in between just to see if possible. Anyways, fine. So, introduction to cryptography. Cryptography is a term. It is the art of rendering a message unintelligible to any
no.
unauthorized party. That means we have to provide information in such a way that the information should reach to the destination without hacked by someone and without
No.
listening by someone. So that is the main intention
Of
behind the
the
cryptography. So someone
fun
else
of
is speaking.
wait.
Shashireka, ma'am.
Yes.
Yeah, fine. Yeah. So now, if you take this particular example, so I had taken small example to specify that. Suppose if any terms are there, B, N, L, O, T, S, D, Q. So this is the term that is given, but actual information is C plus, that means each character plus next character. That means it will be C, O, M, P, U, T, E, R. This is we have seen in the starting stage of cryptography. So if you want to convey any information which is not audible, which is not cracked by anyone, or otherwise to hide from others, if you want to convey any information, so then we used to use this Venom cipher. So this is the way of creating the Venom cipher, and all those things you people know. just adding some 2 bits or otherwise next two characters or otherwise next 9 characters. This is one way of providing the cryptography. And the next another thing is cryptography is a broader field of cryptology. Is I mean a broader that means the main field of the cryptography is cryptology. So which also includes script analysis. That means whatever we are performing the encryption, someone will understand the technology, that means process of cryptography, that is encrypting or decrypting, and he will try to identify the information. So that is called as the art of code breaking. So we have to talk about cryptography as well as we have to take care about the cryptanalysis. The one who will be called as eavesdropper. So he will always try to listen to the information. That is what about the basic cryptography terminology. So coming to the another example that I would like to explain. Suppose later people have used the padding mechanism. Suppose if the message is like if my original message is like I love quantum. Otherwise A B C D E F. I don't want to take much bigger words. A B C D E F. And we used to have the padding 0 1 1 0 1. 10010 10010 sorry 10011 123 and next 11011 11001. Let us assume that these are the 1 2 3 4 5 one more 10111. Let us assume that these are the padding bits. Now if you want to pass the information of ABCD, for ABCD we used to have the key A will be 00001, B will be 00010, C will be 00011, D will be 00100, E will be 00101, F will be 00110. So this way we are going to take the original message. So 00001, next 00010, 00011, 00100, 00101, 00110. So this original message will be XORed with the pad message 01101, 10010, 10010, sorry 10011, then 11011, 11001, 10111. So this will be padded, as we know that the XOR bit is nothing but if both are 00, if both are same 0, if both are different 1, 01100, 10000, 10000, 11111, 11110, then 10001. So this is the ciphertext. That means we are taking the plain text that will be XORed with the pad and which is generating the ciphertext. Further, the ciphertext will be XORed with the pad and it will be generating the plain text. So this process will be recurrent. That means it can happen in cyclic manner. So say plain text plus pad. So this pad will be called as key. Now we have to secure this key. This key is the main term. So all the problems, so that means all the research problems had come, all the research papers and all those things will be on how to secure this particular key and how to transfer the key in the communication channel in a secure manner. So likewise, the same thing. General representation of cryptography. Suppose Alice and Bob, these two people, everyone knows that they are very famous people. In though for those who are in the security field, that is security research field. So Alice and Bob, there are two people. So always Alice will lock the message with some key. Then he will send it to the communication channel, where the communication channel is always insecure. That means we cannot expect what will happen. Someone can take the data, someone can modify the data. So those things will be happening in the communication channel. still we should send an information in such a way that no other person can read our information. That should be the criteria that we have to take care. And once it is reached to the Bob will open with the same key to see the data. So this is called as this is the info. This is called as symmetric encryption. Here we are for locking and opening. We are using the same key. But if the key is known to Eve, then it is gone case. That means the information will be received by the Eve as well. So which should not happen generally. So that is one kind of. This is a class cryptography. The same key will be used for both encryption as well as decryption. Plain text, which is performing some operations, which will be converted with the key, then it will be converted into ciphertext. The same key will be used to perform the decryption. With some operations, it will be regenerating the plain text. So this is the process in classic cryptography. The best example for the classic cryptography is advanced encryption standard. That means AES algorithm, which is a very famous algorithm, which can encrypt the 128 bits or 16 bytes at a time, or with the key of 16 bytes. So hope for Kishore sir also, Gupta sir had taught network security. Is it so, sir?
Yes, sir. Yes, sir.
So
Gupta, sir. Yes, sir.
yeah, he is a very famous person in our Gurdwala Engineering College. He will teach the things of cryptography very nicely with different examples. We have learned it really in a thorough manner. So this is the way plain text. Plain text will be performing for some 10 rounds of operations. So with the key, where key will be changing at each and every round. Finally, whatever the key that is used at the last round will be given as a first round operation. That is for the first round operation in the decryption process. So the first left part is for the encryption and right part is the decryption. The problem is the key. Though it is a 128-bit key, it is possible to crack it. So coming to the next way, here we are going to use two different keys. That means one is called as private key and second one is public key. Public key will be known to everyone. If I have my public key, it is known to everyone in the channel or in ring. But the private key will be known to me only. So it is not possible to identify the private key by anyone. So there are three famous authors, Rivest, Shamir and Nadelman. Sorry, SHAMIR, Adelman. So these are the three famous authors. Those who have invented RSA algorithm, which is called as the public key cryptographic algorithm. So where Alice will encrypt the information with his private key. Okay, and that means then it will be transmitted in the communication channel. Sorry, here it is reverse process. Sorry, Bob will encrypt the information with the Alice public key. So which will be communicated in the communication channel, where Alice can decrypt the information with his own private key, where the private key is not known to anyone else. So if others are trying to open that information, it is not possible because they know only their private keys and other public keys. With the public key, we cannot open the information, but we can lock it. So this is the way of providing the encryption. RSA is the best example for public key cryptography, though there are other different algorithms. So we can see Elite writes a message and Alice finds Bob's public key, and using Bob's public key, he will encrypt the information. Sorry, she will encrypt the information. Alice is the girl. So then it will be passed in the communication channel, and Bob receives. Bob receives the information, but it has to be unlocked. He will unlock the information using the Bob's private key. So Bob's private key will be used to unlock the information. Then he will read the information. So if anyone is encrypting with some access public key, only that access private key will be used to open the information. So now if you take the example of RSA, the RSA process is very simple. It will be having certain steps. So we have to take two prime numbers like P and Q. Generally, it will be very large. I'm taking an example of 11 and 17. These are the two primary keys. Then we have to find the value of n, where n is equivalent to 11 into 7, that is P into Q. That is equivalent to 11 into 17, which is 187. and we have to find the phi of n, that is equivalent to p minus 1 into q minus 1, that is 10 into 16, which is equivalent to 160. Then after finding that, then we can find the encryption key, where the GCD of uh, e comma phi of n must be equal to 1, such that we have to find one value. Let us assume that e value is 7. The GCD of 7 and 160 is 1. E value is 7. Then we have to find the decryption key, where DE mod n equal to DE mod phi of n is equivalent to 1. D mod phi of n only, right? Yeah. Yeah. The same. D mod phi of n equal to 1. So in such a way that we have to find the decryption key. So let us assume that the decryption key in this case it is sum 23, because 23 into 7 is equivalent to 161. So 23 161 mod 160 is equivalent to 1. So this is satisfying. Fine. This is ED mod, that means DE mod and phi of n is equivalent to 1. Then this 7 and 187 is known to everyone. These are my public key, but 23 is my private key. Seven is public key. For encryption, we will use the public key, and for decryption, we will use the private key. Let my public key is known to everyone, so I have no problem. So now what I have to do, suppose if I want to perform any, at the same time I have to know the value of n as well. So n is also known, but suppose if I want to perform the encryption, so m power e mod n. So this m power e mod n, suppose if m is equivalent to some 12, then 12 power 7 mod 187. So this operation we have to perform. So 12 power 7 is a very big number. It is very difficult to. So if the numbers are very big, that means if you want to find 12834 power 7869, then it is very difficult to find the power of mod. So for finding the power of mod, there is a small algorithm provided by the William Stallings. So this algorithm will be used to power a power b mod n. So which will always find the a power b mod n. So there is no time to explain about this particular algorithm, a particular small algorithm. So likewise, this RSA will work. Similarly, at the time of decryption, so suppose we'll get some ciphertext. Let us assume that this is C. Then for decryption, what we have to do? We have to perform C power D mod, which will give the message. So this way we can perform the RSA algorithm. So this is the complete select two prime numbers PQ both are prime. Calculate n equal to P into Q. Then phi of n is equivalent to P minus 1 into Q minus 1. So select an integer such that the GCD of e comma phi of n is equivalent to 1. Then calculate D, where DE mod phi of n is equivalent to 1. Then public key is known to everyone, that means e comma n. Private key is known to me only. Okay, suppose if I want to perform the encryption, so we must ensure that m is less than n, where m is a message and n is a p into q value. C equal to m power e mod n will be performing the m power e mod n will give the ciphertext, and similarly to the at the receiver side, C power d mod n will give the plain text. So this is a simple glimpse of RSA. So same thing I explained. 17 and 11 and 187, 167 and 23. The same thing I explained with you. What are the advantages of RSA? If you're going with the generally RSA on classical computers, it uses one algorithm called as general number field service GNFS for finding the factors. Finding the factors and prime factors is the most important concept in the RSA. Yeah, fine. So then, as well as we know that according to Moore's law, every 2 years the processing power should be doubled. The computing power should be doubled. So we could see how the evaluation of computers have been done from basic Pentium processors with P1, P2, P3 with 777 megahertz to we reach to a position in such a way that where 2 point gigahertz cores of 64 will be there in one CPU nowadays. Anyways, we are calling them as GPUs. So likewise, we are extending our computational power from starting from basic megahertz speed to soon we are going with the terahertz speed. So where the processing computation, not only terahertz, not only one processor is having terahertz. No, we are not bothering about it. So we are going to divide them into cores, where each core will be having certain speed, and we are using them as master slave and all those things. That is different field. I don't want to touch. So likewise, the technology is going. But what is the next upcoming? And anyways, it is started also. People are trying to bring the quantum bricks. So nowadays, if proper quantum computing is established, till now we have the uh, just we can trust the RSA completely. We have the what we can say. We have the trust on the trust that we are sending the information in a communication channel where the information is secured properly. So if the number of bits are 1024, if the key size is 1024 bits or 2048, it will generally take months to years. And if it is 2048 or 4096, it will take hundreds of years with the current computation power. But what if quantum appears? So you might have seen the Shaw's algorithm yesterday. So Shaw's algorithm, if it is not done, fine. Don't worry. Tomorrow, I think I had seen the Shaw's algorithm in your topics of topics that are going to be covered in this particular FD. Yeah, people are using the Shaw's algorithm will be used by the quantum. It's a quantum algorithm. It can easily find the large factors of large numbers easily. So and 10424 bit RSA can be cracked in just hours or days. And if it is 2048 bit RSA key, it can be cracked in weeks or months. That means no way the RSA is in safe position. There is a threat for RSA. So till now we have Barosa on the RSA completely. So that means, but now when quantum completely established, we cannot say that the quantum, the RSA is secured. So we have to secure the key. Then for that purpose, there are two different authors. I could always forget those two authors. Let me explain about those two authors. There are two authors called as yeah. So Charles Bennett and Gilles Bassard. In 1984, they have introduced one protocol called as, so the protocol name is B, B, and 84. That means they brought one protocol called as BB84. This is how BB84 protocol had come into picture. So, and as we know that quantum will always work with the photons, not electrons. So we are not passing the information in secure channel. We are passing the information in quantum channel. So how quantum BB84 protocol will work? So can anyone tell me? Should I explain the example initially on the board? That means this one note and go for PPT, or is it okay if I cover only PPT?
So once you can explain on the board, sir.
Yeah, thank you.
Sir, as time permits.
Yeah, half an hour. Anyways, half an hour. Yeah, one
Yeah,
note
you
I will
can go ahead.
explain.
Yeah, sure, sir.
Yeah. So let us take an example. The quantum will be, you know that there will be I cannot draw the diagram properly. So there will be the information can go in vertical, horizontal, and diagonal. So if it is going with 0 degrees, we'll call it as 0 bit, and if it is going with 90 degrees, we'll call it as 1 bit. And if it is going with 135 degrees, 45 degrees, it will be called as positive, and if it is going with 135 degrees, it will be called as negative. And 270 is 0 again, and 360 is 1 again. And similarly, 270 plus 35, 45, what is the value? 315 is positive, and 360 plus 395 is, sorry, what is that? I can say. Sorry, this is 315, 360. Yeah, fine. Anyways. Sorry, 180 is 0. After 180, then we have to go with 225. 225 is positive. Then 270 is 1. Then 315 is negative. And 0, again 0 is 0. That is 360 degrees as 0 will be always 0. So this way the data representation will be done. I'll take one clear example how this data formation will be done. I have taken one example. Let me take the same example here. Yeah. So take Alice bits as, assume that there are two people, Alice and Bob. So let me explain this small PPT. You will understand so that I'll go with the explanation. There are two people. One is Alice and second one is Bob. It's very easy to understand this particular protocol. Just observe it. Alice and Bob are there. They want to transfer the information, and for the process of encryption and decryption, they wanted to use the same key. So assume that it is a symmetric encryption only. So then what Alice is doing, Alice is taking two bits. One is Alice bits and second one is base bits, A and B. Then, so all these bits are generated randomly. So let us assume that the information generated by the Alice bits is Alice bits are, let us assume that any random value. I'm not taking any particular example only. If I take example, then you can easily understand also. That's also fine. 0, 1, 0, 0. 0, 1, 0, 0. 1, 1, 0, 1, 0. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let us assume that n equal to 9. That means I want to generate a key of length 9. I don't know finally how much it would be. Then Alice basis. So this will be called as A. And Alice basis will be B. This is also random. I'll generate randomly. So where 1, 1, assume that it is 1, 1. 0, 0, 0. 1, 1, 0, 0, 0. 1, 0, 0, 1. In general, it will be represented as X, X, Z, 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 X, Z, Z, X. Some people will represent as cross mark and H. That is anyways. My representation is X and Z. So let us assume that Alice bits are X and Z. I want to explain about ones and zeros also. Then I'm going to generate a stream of quantum bits. Qubits will be called as. The qubits will be generated. If it is 0x, that means it is towards positive. So actually it is 0 towards x positive. Then 1 to x, it is negative. From 1, it is going towards the negative side. Then 0, 0, it is 0 bit. 0, 0, it is 0 bit. There is no change. Then 1 0, that means 1 0 also it is 1. 1 1, it is negative. Then 0 0, it is 0. 1 0, it is 1. 0 1, it is positive. So this is created based on the basis. And there are bits, bit equal to 0, bit equal to 0 and bit equal to 1. And we have one is Z and second one is X. Yeah, same thing is X. If it is 0 and it is going towards horizontal direction, that is Z towards 0 direction, then it is 0 only. If it is 1 and if it is going towards that means horizontal or vertical direction, that is 1 only. If it is 0 towards X, then it is positive. Sorry, it is quantum bits. Then it is positive. If it is 1 towards X, it is negative. So this way, we are going based on this particular truth table or this particular basis, we have constructed this one. It's completely random. All these bits are random. These allies bits are random. Only randomized algorithm. And this one is random. Okay, some places they will mention it as ones and zeros, and some places they will mention it as X and Z. So see, I'm going to explain this particular part. There is a X gate, that is Z gate, and there is Herman gate. Okay. So now if A and B are 0 0, that means allies bits are 0 and basis is also 0. That basis 0 I represented with Z and 1 is represented with X. Then quantum bit will be 0. Then if it is 0 and 1, then it is towards positive direction. And if it is 1 and 0, then it is towards 1 and 0, then is allies bit is 1 and it is going towards horizontal or vertical. We can decide. So it is 1 only. So 1 1, it is negative. So previously, whenever we are communicating in the normal regular channel, we can transfer the information. How I can say, we can transfer the information either zeros or ones. Only the sequence of zeros and ones used to be transmitted. But now we are transmitting 4 different combinations. What are they? 0, positive, 1, and negative. That means either direction of the photon. That means the direct photon will always rotate and go in the quantum channel. So the direction of photon will be horizontal means it is 0, vertical means 1. Also, diagonal values will not be used for any purpose because we cannot decide whether it's 0 or 1. It is having 50-50 percentage. So the diagonals will be have to be ignored. So let us assume that this is the status at this. So am I explaining properly or am I going in detail? Can anyone just tell me if it is not required in detail? I'll go on superficial level. Is it fine if I go at this stage? At this
Yes, sir. This is
phase?
fine, sir.
Yeah, fine.
Thank you, sir.
Thank you, ma'am. Yeah. So now we got the qubits. Yeah. Otherwise, let me create a small table kind of thing, which will not confuse anyone. So allies bits, allies basis, representation of the same thing in the form of X and these qubits. Till now we are here. So how many bits are there? 9 bits are there. So 1, so 2, 3, 4, 5, 6, 7, 8, and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fine. So allies bits are these are 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 1 0 0 1 1 0 1 0. Basis, this is A and this is B. We are expecting as of now 1 1 0 0 0 1 0 0 1. And coming to the representation of X and Z, this is X X Z Z Z X Z Z X. Fine. And then coming to the qubits, the qubits will be plus, minus, 0, 0, 1, minus, 0, 1. It is plus. Yeah. Now we got the qubits. Let us assume that the qubits are communicated in qubits are transmitted in the channel. So assume that the qubits are transmitted in the channel. So the channel, the data has been transmitted. Yeah. Now at the receiver side, there is a Bob. Bob will also generate one random sequence. It will be called as B dash. Bob bits, Bob basis. It will be called as Bob basis. So let us assume that Bob basis is it's also random. Yeah, I'll take the same example so that I want to explain about the eavesdropper as well. Yeah, Bob's basis will be 1 second. Yeah, Bob's basis will be 1 0 1 0 1 1 0 1 1. 1 0 1 0 1 1 0 1 1. That means in the representation of X and Z, it will be X Z X Z X X Z X X. So this is a Bob's basis, which is not same as Alice basis. It's because it's also random. This is random. Anyways, both are same. This is also random. And this is also random. All are random only. But how key will be generated now? That is the question. Now we are going to compare whether Bob's and Alice one is matching or not. If Bob's and Alice one is matching, Bob's basis and Alice basis is matching, then that particular bit will be considered. Why means, see, if one is horizontal and one is diagonal, we cannot say whether it is 0 or 1. There is a 50-50 percentage chance. Understanding? So now I'll explain. The Bob's basis has been created. Now the information of qubits has been transmitted in the channel. There is a Harman gate. So now we are going to create another truth table in such a way that if A and B is 0 0, then it is qubit is 0. If 0 0 is there, then the qubit is 0 itself. If Harman gate is 0, there is no change in that qubit. If A is 0 0, the qubit is 0, but Harman is 1, it will be changed to positive direction, as I explained from the same table. So you might have seen basis 0 1, and this is X and Z. Sorry, this is G and this is X. Yeah. 0 Z is, it is 0 only. 1 Z is equivalent to 1 only. 0 X is positive, and yeah, I can do like this. 1 X is negative. XC assume that it is 1 and Z assume that it is 0 from this truth table. So 0 0 it is 0 only. 0 1 Harman gate will change it to positive. 0 1 is positive and Harman gate is 0, so it won't change. It is positive only. 0 1 is positive. 1 and Harman gate is 0. So then in this case it will be changed to 0. That means from positive to 0 it will change. Sorry. 1 0 is 1 and there is no change, 1 only. 1 0 is 1, 1 1 is negative according to the truth table. 1 1 is Negative. Negative 0 is negative 1. 1, 1 is negative. Negative 1 is 1. So negative to 1. So that means you have to imagine always there are horizontal and vertical direction and diagonal direction. So fine. According to this truth table, so now originally plus is there, plus and x. So plus and 1 is nothing but what will happen? Plus and 1, it will be changed to 0. You can see. Yeah, 1 0 is plus and 1 will be changed to minus. Sorry. Yeah, I'm sorry. 0 1 1. It will be changed to negative. Yeah, correct. 0 1 1. 0 1 1 is plus and 1 is 0. Fine. Plus and 1 is 0. I'm sorry for that. So here what you have to observe is you need not observe much. You have to observe one thing. If there are B and B complement both are same, B and B complement both are same is nothing but the same thing will come into the side dash. So this here B and B dash is not same. You need not bother about it because it is a 50-50 chances. It won't give the proper value of either 0 or 1. Here also B and B dash both are not same. So see this is also 50-50 chances. B and B dash are same. So the same 0 has been here. B and B dash are same. The same 1 is here. 50-50 chances. 50-50 chances. 1 on 1. The same 1 will be here. So according to that, if B and B dash are same, X and X, the same bit will pass here. That means 0 will be passing here. Then uh, here B is X and this is Z. Both are not same. What will happen? 1 1 is negative. Negative 0 is 1. No, not 1. It is negative 0 is uh, what is that value? 110, right? 110 is negative. Yes, sorry. Negative 0 is negative only. Sorry, why I'm thinking this much? Fine. It is 0 1. Both are not same. Z and X. That means Bob and Alice didn't identify the bits properly. So I'm marking all these things with red. The different ones. This one also different. Z and X. So 0 0 is Z. Z1 is positive. This bit is positive. Then ZZ both are same. So it will be 0 only. Directly 0 will come here. Then ZX both are not same. 1 0 is Z. 1 0 1. It is 1 0 is 1. 1 is negative. You can see from the truth table 1 1 is negative. It is. Yeah, good. So it is also not matching. This is Z and this is X. Both are not assumed the correct key. Now, then what will happen? X and X both are same. 1 1 1. So 1 will come as a 1 will come here. Then Z and Z both are same. That means 0 0 0 will come here. Then 1 0 1. That means 0 and 1 both are not same. So 1 0 is Z. Z1 is negative. It will be negative. This is Z and this is X. Here both are same. What is the value? Both are same in the sense 1 1 1 1. So finally, user can understand either 0 or 1. Other than thing, nothing, he cannot understand all these positive and negative because it is to give 50-50% whether it's related to 1 or 0. We cannot identify 50-50 for 1, 50-50 for 0.
Sir,
So,
is that last one is not zero?
yeah, 0, I'm sorry. Thank you. Yeah. Thank you, ma'am, for following. Yeah. So this is also 50-50 chance to become it is 1. This is also 50-50 chance to become it is 1. So what we will do is we will ignore these terms. So this one also will ignore and remove. Now, what are the positions? 0, 1, 2, 3, 4, 5, 6, 7, 8. So what are the positions considered? We have considered the positions of 0, 1, 2, 3, 4, 5, 6, 7, 8. So these are the positions that we have considered. Now for the encryption purpose or decryption purpose, these are the key values. And Alice and Bob can tell that. So consider only these positions through phone also. I can call to Bob can call to Alice and Alice can call to Bob and say that consider the bits of 0, 3, 5, 6, 8. What is the values of 0, 3, 5, 6, 8? It is 0, 0, 1, 0, 0. No one knows that is 0, 0, 1, 0, 0. Only Alice knows or either Alice knows or Bob knows. No eavesdropper can understand this particular terminology. So that is the beauty of quantum bits. So that is this is the way. First of all, now how to know whether eaves exists or not? How to know whether eaves exists or not? So this 00100 will be called as key, and Alice can use for encryption. And whenever the Bob receives the message, he can use it for decryption. Now we can perform AES of 10 rounds or 10 rounds, and the message will be strong. No one can decrypt without knowing the key, and the key will not be revealed to anyone.
Excuse me, sir, but Bob's bits are different, right? 10101, right? So they won't consider Bob's bits directly.
Where are the Bob's bits?
Like the random bits chosen by Bob in those
So
positions.
this one, finally bits are these one. Those are
So
basis.
we won't consider the one on the initial
That is
one.
randomly generated. That one will not be, we won't bother about it. So finally, we will bother about these bits.
Okay, sir, thank you.
This is key. And this is key. Clear, sir?
Yes,
So
sir.
here bases are secret, sir.
Basis is random. Basis can be anything. Basis, it is my assumption. I'm assuming this one is me. But if any eavesdropper and comes and assumes, that's what I'll explain with the eavesdropper as well. Suppose eavesdropper assumes something in between. I'll explain with that also. Just 1 second. I have one example. I had kept one here. Yeah, let us take this example.
Sir, one small question.
Ask me, please.
Sir, with this much of randomness, how do we ensure the accuracy of message conveying or message receiving? Because basis one is also from Alice side, basis one is also random, Bob side also it is random. So there is too much of randomness involved, right?
Yeah, that is the beauty, ma'am. Even such that much of randomness is involved, we could generate the key which is same at both the sender side as well as receiver side by using this process.
And in spite of some of the positions being ignored and this much of randomness, still we are able to receive the accuracy.
Yes, yes, ma'am. We shall try with random example. I have created one program as well. 1 second. Let me open it. Collab research. So, yeah. Hmm, 2 minutes, ma'am. I think it is importing the random. Yeah, fine. Yeah, fine. So let us assume that now alias bits we shall take not this much. It will be very difficult to explain. The 24 bits is very. Can I take some 9 bits, ma'am? Yeah, 9
Yes,
bits.
sir.
What are the allies bits, ma'am, here? 0, 0, 1. We shall run it once again. There are more number of zeros. One more time. Why? One more time. Anyways, fine. Now I don't want to trouble much. So 0, 0, 1, all zeros. Am I right, ma'am? One more last thing.
One more zero is there. One more zero is there, sir.
Yeah. Double zero, triple zero one. Double zero, triple zero one. Yeah. So this is basis, I'm assuming. I'm using ones and zeros only. I'm not bothering. Then Bob's, then it is qubits. Let us assume that this is qubits. Then it's Bob's assumption and Bob's key or Bob's bits, we can say. This is Bob's basis, B complement. This is LS basis, this A, B, and this is A. And this is Bob's key, A complement. Let us assume that. Now you have to make sure that A and A complement should be same. Based on the matchings between B and B dash, we have to check the bits that are B equal to B dash. Other bits are useless. Now what is that? XZZ, XZZ, XZX. So 1 0 0, then 1 0 0, 1 0 1. This is also random. Clear, ma'am? So 0 1, it is positive. 0 0, it is 0. 1 0, it is 1. 0 1, it is positive. 0 0, it is 0. 0 0, it is 0. 0 1, it is positive. 0 0, it is 0. 1 1, it is negative. Clear, ma'am? B dash,
Yes,
Bob's basis, ZZ.
yes, sir.
So 0 0, 4 ones, 0 1 1. This is Bob's basis. Now, if both are not same, B and B dash are not same, then it'll 0 1 0 means what it will come? 0 1 is positive, positive 0 is positive only. Then both are same, so 0 only it is. Then both are not same. 1 0 1 is negative. Then 0 1 1. So 0 1 is positive. So 1 1 both are same. So it is 0 only. 0 1 both are not positive. It is so both are not same. It is positive. 0 1 both are not same. It is
Positive.
positive. 1 0 both are not same. 0 1 0 means it is 0 1 is positive. Positive 0 is positive only. 0 0 1 positive. Then both are same. It is 1.
Negative.
Got it, ma'am? Now,
Yes,
so
sir.
which one we have to consider? If both are same, what are the what are B bits and so here both are same means what are they? So this one is
Second
same.
one,
Second one and
fourth one,
yeah,
fourth
fourth
one,
one and last one.
fifth, sixth, fifth and sixth.
Both are not same. B and B dash are
Huh.
different.
Not in sir. Last one.
Last one. Only 3 bits. So my key is that means these 3 will be considered. And okay, I'll keep blue color for this. These 3 will be considered and rest of them will be ignored. This is ignored, 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 this is ignored. Now I'll call to the I'm a Bob. I'm called to the allies, and I'll say, consider first bit, third bit, 4, 5, 6, 7, 8, eighth bit. 1, 3, 8 only consider. Remaining bits you ignore. So what is my key now? A 0, 0, 1 is my key. Here also 0, 0, 1. Here also 0, 0, 1. But eavesdropper cannot identify whether 001 or 010 or what it is. If I call to the allies and say that 138 bits are consider you consider 138 bits, Eves cannot identify because all these bits are generated randomly. Is it clear, ma'am?
So superposition bits which we are not considering means it's just to confuse.
Yeah, just to confuse the E's.
Okay.
So only 138 positions are considered. Yeah, here we had taken I had written the code for this 24 bits, n equal to 24. So that's why it is, uh, yeah, it should be 9. Yeah, you can see 001. So this only 238 bits are considered here with this example. So my key is 101 and Bob key is also 10. Now consider an example with use. For example, if you take, what is the time? Yeah, still half an hour is there. I can extend the code, no issues. Let me take the example of with use, whether Eve exists or not, eavesdropper exists in the channel or not, if I want to identify. So fine. Now allies bits. Allies basis. Then Eves, then qubits. These are the qubits. Okay, fine. Then Eves basis. Eves qubits. Then Bob's basis. Finally, Bob's qubits. That means key. Now, consider some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Even it is not our lucky number, we have to take 13 numbers now because there is no other option. LS, these are A bits, or otherwise I can say it is a key. So 13 bits, right? I'll write for 13 now. Right. So 00150. So 1 second, I'll run again. Why it is that random number generation is not correct, proper. It's generating the same thing. I don't know bother about it. 00100 or 11010001101. Let us assume that this is my random key. And XG, GX, XXZ, XZ, GX. Sorry, we are taking zeros and ones, right? Sorry, I don't want to confuse again. 1 0 1 1 0 1 1 0 1 0 1 1 1. Let us assume that this is basis B. Now qubits we have to generate. How the qubits will be generated? 0 1 is nothing but it is positive 0 0 0 only 1 1 negative 1 1 negative 0 0 0 only 1 1 negative 0 1 positive, then 0 0 0 0 1 0 1 is uh, it is positive 1 0 it is 1 1 1 negative, then 0 1 positive 1 1 negative. Now Eve has entered into the market. He has created some random numbers. Some assumption he has done, and he has created some random numbers like 0 1 1 0 1 1 0 0 0 1 1 0 0. Let us assume that. Now 1 0 1 0 from our truth from our yeah, I cannot I don't want to apply mine all the time. So 0 1 0 it is positive. 0 0 1 0 0 1 is it is positive. Then 1 1 1 it is 1. Then it is 1 1 0. 1 1 0 is 1 1 0. What is that? Negative, and it is negative. 1 1 0 is negative only, right? Yeah, correct. 0 0 1 it is positive. Then 1 1 1 it is 1. 0 1 0 it is positive. 0 0 0 it is 0. 0 1 0 it is positive. Then 1 0 1 1 0 is 1 1 1 negative. Then 1 1 1 negative negative 1 is 1. 0 1 0 0 1 0 is 0 1 is positive, positive 0 is positive. Then 1 1 0 1 1 0 is negative, negative 0 is negative only. Yeah, correct one. This is Eve's qubits. That means he changed the qubits in the communication channel. So LIS had sent something. This is X. Let us assume that X has been communicated in the. So in between Eve had come, he changed it to Y. Now these qubits have been transmitted in this. This Y bits have been transmitted in the communication channel instead of X. Y bits have been communicated as transmitted from this particular position. Till now X is there. Now Y has been communicated. So Bob's random message will be there now. Bob will be having some random message. What is the Bob's random message? Let us assume that I'll take another color. So yeah, 1011 0 0 0 0 1 0 1 0 1. Let us assume that this is Bob's random message. Then what will assume 0 1? That means this positive 1. Positive 1 is nothing but what is the value? Yeah. Okay, sorry. He got these qubits, fine. So 0 and 1 both are not same. That means Eve's bits. These are the Eve's bases. This 0 1 both are not same. That means 0 1 both are not same is nothing but positive 1. What is the value? What I can say? 0 0 0 1. Yeah. 0 0 1. What is the value? It is positive. Let us assume that this basis, sorry, this B is communicated in the communication channel. B can be sent in the public. So let us assume that this B has been modified in the public channel. Sorry, this is X. This has been modified. Sorry, I'm this part I little confused. So B has to be communicated. So you can see this diagram. You can understand B can be transmitted in the communication channel publicly. So no anyone can see B. There is nothing wrong. But Ali's key will not be known to anyone, and the qubits will not be known to anyone. Okay, so these qubits will not be known to anyone. So actually, these are the qubits that has to be generated with the B. But because E has modified the B, what I will get 0, 1, 1. Sorry, 0, 0, 1. 0, 0, 1 means what will happen? Positive. Yeah. Then 0, 1, 0. 0, 1, 0 means negative. Then 1, 1, 1. 1, 1, 1 means it is 1. Yeah. Good. 1, 1, 1 is nothing but it is 1. Yeah. Then it is 1, 0, 1. 1, 0, 1 means negative. Then 0, 1, 0. 0, 1, 0 means positive. 1, 1, 0. 1, 1, 0 means it is negative. Then 0, 0, 0. It is 0. 0, 0, 0. It is 0. 0, 0, 1. It is positive. 1, 1, 0. 1, 1, 0 is negative. 1, 1, 1. It is 1. 0, 0, 0. It is 0. 1, 0, 1. This is negative. Now, these are the qubits generated by Bob. Actually, Bob qubits. This is the key actually. What are the matching things? This will not be matched. This will not be matched. One will be considered because it is matching. According to considering that EU message. Considering that EU's message, it will be matched. And it is not matched. It is not matched. It is not matched. It is matched. Matched. Not matched. Not matched. 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 Not matched. So what Bob will tell, consider second, 3, 4, 5, 6, sixth bit, seventh bit, 8, 9, 10th bit, 11th bit. Those values are 1, 0, 0, 1, 0. This is my key, he will say. What is LI's 0, second bit? 1. Sixth bit, 3, 4, 5, 6. Sixth bit is 0. Seventh bit, it is 0. 10th bit, it is 1. Yeah, this one is 0. Actually, here Bob has identified the bit section. No, the random number is similar to the is matching. But anyways, since we had taken very small number, 10010, it has come. So this is key. But generally, let us assume that because of some it is a long number of 1024 bit or something. Some is because of some misinterpretation, it has come as 11010. Now what Alice will do? He will do encryption with this particular key, where Bob will decrypt the information with this particular. So which is not matching. Or Bob encrypt with this particular key, and Alice decrypts with this particular key. So the information is mismatched because we have taken only 9 bits. Because of that, the bits might have matched, but generally the bits will not match in any case because there is a theorem called as no cloning theorem. No cloning theorem will be in quantum mechanics. It is saying that it is impossible to create the identical or perfect copy of quantum state. So this theorem is saying that it is very difficult to generate the similar kind of qubits at any cost. So that is the beauty of this quantum. So since we have taken only 9 to 13 numbers only, so that's why the zeros and ones might have matched. But if you go for 1024 bit or 2048 bit key or 128 bit key, definitely there won't be any match. So now assume that. Now what will happen? Bob will say that he will encrypt and he will. So here the beauty is Bob can call and say that consider these bits. But encryption and decryption, we are not receiving the same information. How these Alice and Bob will know whether it is properly encrypted and decrypted or not? For that purpose, another theory is there. Suppose if you have generated the 1024 bit key randomly, out of that, let us assume that 596 bits have been final key, and remaining have been ignored or removed because of mismatch of B and B dash. There are 596 bits. What quantum theory is saying that give half of the bits, identify first half of or second half of the bits. What is 596 by 2? It is the 298. Give 298 bits to Alice and say that these are my first 298 bits. Are they matching with you? If these 298 bits are matching, then there is a guarantee that the remaining bits are also matched. Very less cases, these 298 bits also will match with E. There is no case that these 298 bits will be matching with these even the Eve knows these 298 bits, he cannot do anything. So that is the beauty of so what they are saying is share half of the allies, whatever the key in your Bob, and allies also will share half of the bits. Check whether both are matching or not. If they are matching, assume that the rest of the key is fine. In very less cases, the rest of the key will fail. In very rare cases, these first 298 bits will match with the EU. That is the beauty of this quantum key distribution. So that means the key cannot be known at any cost between by the EU, and EU cannot if the information is not matching, the 298 bits are not matching, then I can say that wait for some time. The communication is not safe at this time to send the information. We can send it later, and we can complain, or we can say that there is a hacking mechanism involved in my channel, and all those things can be specified. Ma'am, is it clear? Am I making sense here? Can anyone respond? Is it fine? Is it...
Okay, sir.
It's okay.
Yes, sir. Please carry on, sir.
Yeah, fine. This is what about that. So now what I had done is I don't want to prepare much PPT, which is unnecessary in case of mathematical operations are there. So I had taken simple program. A simple program has been written. Don't worry. These days to write the programs, I'm using mostly our GPT, our OpenAI. Whenever the technology is there, we have to utilize it. So import random, I have changed the code slightly. Okay. Import random, it is done. Define random bits. That means randomly whatever the bits that is there. So this particular function, what it will do is it will generate random numbers from of zeros and ones for n values. N already we have passed it. Fine. Then basis will be x and z. So you can give 0 or 1 also. That is also fine. Anything is fine. 0 or 1. Then encode labels. That means encode labels is nothing but if B equal to Z, that means bits and bases we are passing. Bits will be B and bases will be B. If B equal to Z, directly 0. If B equal to, that means if first bit is 0, that means you can say that this is Z means if it is 0, 0 will go. If it is 0, if it is 1, 1 will go. The same thing has been done. So if B equal to 0, append 0 like this, else append 1. So this is the code of this one. If B equal to X, that means if this is X, then again there are two options, 0 and 1. If B is X and it is 0, then append positive. It is append negative. So the same thing has been done. Positive if B equal to 0, else negative. So this is this particular code will be used to encode the labels for bits and bases. And this code will be used to identify if Alice basis and Bob basis is same or not. Keep yeah. In this case, oh God, I expected this. Is it fine? Am I visible?
Yes, sir.
Yeah, the system was set. Don't worry. Is my face is visible, ma'am?
No. Yeah, now.
Yes, sir.
No, it's not that. So fine. Let me share this. Sir, can you give permission to share? Is it visible, sir?
Yes, sir.
Visible, right?
Yes, sir.
Yeah, fine. Yeah. Hope this code is also visible.
Yes.
Yeah. As I said that here we can keep it as a 0 or X. 0 or 1. Accordingly, I'm changing this code also if it is 0. Yeah. This is one. And next one is B and B dash are same. Then consider the alias bit as a key. Otherwise, ignore. So that is a part of this one. Yeah, fine. Now shift. What it will do if alias basis and Bob basis are same, identify those indexes and keep those indexes in keep index. And take the alias bits from those indexes and take the Bob's bits from those indexes. That is the keep index, whatever you keep index that is constant. It's a list and it is a list and it is a list, three lists. Keep index is a, if you want print, I can print also. Print the keep index. Anyways, it is going to print it. Yeah, keep index is also printed. Sorry, I need not require, it is not required actually. Yeah. Now, np.random. So everyone knows that random.random, what it will do is random of 42. Does anyone knows why 42 will be given in many of the, that means whenever we are generating the random number? There is no theory behind it. The author is watching a movie. So in that 42 is a famous number he identified and he are given. So that is there is no logic behind giving the 42. It's a blind logic. So fine. So n equal to 24, which is going to generate 24 bits. Show rows is equivalent to min of and comma. Anyways, we had given the 24, so we need not bother about it. Then alias bits equal to rand bits of generate the 24 random bits. And yeah, using that random.rand equal to 42. That means alias basis. This is A. You can assume that in our example, this is A. Sorry. In our example, this is A and this is B. And these are qubits. These are qubits. That is, those are encoded limits. So I'm considering Eve equal to false. That means Eve is not there. E1 is false. So it will be Alice bits and the Bob Alice basis will be considered as send bits and send basis. That means the data will be transmitted in the communication channel. Send bits will be sent to Alice bits will be yeah, we can send it. Sorry, Alice basis can be sent it to the communication channel directly. Send basis can be done. Then Bob basis again it is random. It is randomly done. 24 values. Then send bits, send basis, Bob basis will be considered as bit, basis, and Bob basis, and it will be called to the measure bit function. These measure.
Server muted.
So it's visible, right?
Yes, visible,
Yeah, it's
visible.
visible.
Yeah. So we are taking the Alice and Bob same bits. Alice and Bob same bits we are taking. In this case, fine. Now, if you consider this this function is used to just display the information in the form of rows. That's it. Just to display the information in the form of rows. So first I'm printing the alias bits, row of alias bits. In this particular row, we are printing the alias bits. You can see these are the 24 bits 001, 00001. All these are. If you want, I can explain with the 13 bits itself. That is good actually to understand. Yeah. This is the 13 bits 001 501 000. And alias basis is 000 1011 001110. 00 is 0, 00 is 0, 10 is 1, 01 is positive, 00 is 0, 01 is positive, 01 is positive, 00 is 0, 10 is 1, 01 is positive, 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 0. So this is the data. These are the qubits. Then Bob random is different from the alias basis. Bob basis is different from the alias basis. You can see it. There is completely different. Then if it is 0 bit is coming and 0 is there, if both are same, it is 0 only. That is Bob results. This is 0. Then both are not same. It is yeah. Here also both are same. Sorry, both are same. Bob basis and alias basis. Yeah. 001, right? 001 means it must be positive. Bob bits. Where this code is there for Bob bits? Here what to, instead of measure bit, we have to call that function called as anyways fine encode labels. Let's leave it. So these are the Bob results we got 00111000 and all those things. If both are same, we are considering it. That particular bit. If both are different, we are ignoring it. So finally, matched indices are 0 to 610. There is a small change in the code. 0 to 610 is nothing but 0, 1, 6 is 0, 10 is 1, 10 is 0. So these bits are considered for passing it to the, for considering it as a key for encryption as well as decryption. So this is the way of doing the qubits. The only problem with this particular quantum qubit quantum key distribution is, so generally whenever we are passing the information in the quantum channel, there might be a noise. Because of that, if qubits are changed, it will happen very rarely. But if qubits are changed, then the information, that means the Alice and Bob cannot identify the suitable bits. Anyways, that's why the half of the bits is always better to be compared to overcome this issue. So generate the key at both Alice side and Bob side. Take the first half from Bob, both compare. If they are matching, consider that the remaining bits are also same. But if noise is there in the quantum, no one can do anything. So that is the only drawback with this particular process. Sir, is it fine?
Fine, sir. Fine, fine. Thank you. Fine, sir.
Yeah, any queries now out of this? Any queries or any oral feedback can be given? Because you
Sir,
people can unmute yourself.
yeah. If adversary always interrupts this communication channel, so there is a chance of mismatch between Alice and Bob's secret keys, right?
Who that Eve changes the
Eve,
information, huh?
yeah. Uh-huh.
Yeah, that's what. Whenever Eve entered into the communication channel, we'll verify. So whether first half is matching and second first half is matching or not, based on that, we'll assume that second half is also matching. If there is no match, we'll take care of the communication channel immediately. We'll provide security
What's
for
the
that
probability
communication.
of if the first
That no
half
one
is
can do
matching,
that.
what is the probability that the second half
That is Eve's
is not there
capability,
yet?
ma'am. Yeah, that is Eve's
Okay.
capability. Eve is capable of entering into that network that no one can do anything.
Okay, sir. Thank you. Thank you for this session.
So there is always a minute chance of the first half being garbled by the eavesdropper, right?
First half or second half. Or
Even if
maximum,
it
if
first
half of
half.
the bits are compared, half of the bits are compared means any half, you can take in random values or randomly also. Any half, if it is compared with the LIS key, then we can ensure that EV is not entered.
Maybe the beauty of this algorithm is solely relying on randomness.
Yeah, ma'am. Completely randomness and beautifully key will be identified.
Equally, the risk is also there. Even if the first half is garbled by the eavesdropper, there is no way we
But
can
nowadays,
identify.
I have explained with 9 bits and 13 bits now. We can go with 1024 bits, 4096 bits. So at that time, it is very difficult to match the half of those bits. The probability is almost very 0%, nearly zero.
Maybe unless we see the practicality, we cannot actually comment on this. But yeah, too much of
Yeah, once
equally the
quantum comes
beautiness
into
is there
picture,
at the
we can
same.
use this. Once quantum comes into picture, we can use this protocol.
Yes, sir. Yes, sir.
Quantum is properly established. If photons are transmitted in that quantum channel, there is a separate channel for this actually. So very beautifully, some videos are there. I'll share one of the video in the group with
Sure.
sir, and he will show that the quantum is see only we are sharing the Bob key, Bob basis in the public. It will be there in the public. You can modify only the public one. Quantum data, no one can modify.
Correct. Sir, one more thing. There is a question in the chat window. What is the means to reduce the noise to overcome this problem in quantum key distribution?
That quantum researchers have to think on quantum mechanics people. So that is not our vertical. So our vertical is only security. Correct, no, ma'am. So these fiber optics and the communication channels all will be taken care of by physics researchers.
No, is it going on in that line?
Any
The
other
research is
queries?
going on in that line.
Yes, ma'am.
Are there
The
any practical
quantum.
applications?
It will take little 1 hour. It will take little time, ma'am. But once the quantum is completely, the bricks are completely established, quantum computers are coming in. So practically it is possible, ma'am. So then they will identify noise, how to overcome the noise. They will start because it's light only, right, ma'am? Light transmission.
So one more question, sir. Are there any practical applications of quantum key distribution in the chat window? This is the question.
Yeah, there are people are using nowadays post quantum cryptography. There are many papers. We also have published one paper recently in one conference. Sir, yeah, there are many papers. Any other? What is the means to reduce? Sir, Matthew, sir. So there are many works going on medical imaging cryptography and financial cryptography through this quantum key distribution. But to utilize it properly, since we have to send the qubits through quantum channel, so the quantum computer must be available at both the sender side as well as receiver side. That is the only that quantum communication must be established. And this BB84 protocol is developed in 84, but still it is not used because of this quantum unavailability.
Sir, hello, sir. Good evening. Myself, Dr. Jain Babu.
Yes, ma'am. Yes, sir.
Sir, here we assume that Eve also having quantum capabilities, right?
Yeah.
Can I assume that he's
No,
having
ma'am. No, sir. Light cannot be modified. That means the quantum channel cannot be modified because it's light transmission, photons transmission.
So Eve can have this quantum capabilities, right? If he is attacking on quantum system, definitely the Eve should be assumed in a system model that he is having quantum capabilities.
But right? He has to establish that quantum machines in between the channel, right?
Yes, sir. Means he tried
so
to.
He has to break the communication channel and he has to enter.
Not breaking, but he will attack something or actual communication will be disturbed. That is using side channel attack or any other attack with the quantum capability. So, what is the probability of that avoiding this side channel attacks in this case? In that case,
actually, sir, this can be further in future research. We can try. So once if quantum mechanics is completely established, quantum computers come into picture, reality, practicality. So when the data is transmitted, if anyone is interpreting how to handle it, that studies can be done, sir. Practically, after seeing how much probability the team can change the information.
Yeah, practically, see, quantum computer is not existence. Then how you can see practicality nowadays? But proper analysis is required. Because I am also working in quantum cryptography. So
that
we
area
need to
I didn't focus on that.
Take consideration of Eve capabilities also. Eve also as powerful as the sender and receiver.
Yes,
and sometimes
Eve,
more than
yes. Nowadays, see, general communication channel will be having routers and the switches and those things, sir. So,
yes.
Because of that, he can enter into.
That's what side channel attack will definitely. You are saying in this example, this protocol is everything is transferred in the form of bits. So when there is a side channel attack, so the bits will be jumbled simply with side channel attack. So actual communication will be
even if there is a change in the data, but it is changed in that if that means the data is transmitted. So it will not match with the. That means whenever it is created with the LS key, so it is not matching with the Bob's key, right? So Bob will assume that there is a key will be disturbed.
Actual data will be also disturbed now. That's what I'm saying. That's it.
Without confirming the key, we are not transmitting the data. Data will be transmitted in the normal communication channel. Once it is encrypted, if you use AES, and if you encrypt and send in the channel,
yes,
it is not possible to decrypt in pure. Anyways, quantum computers comes means we cannot rely on that.
As of now, it is assumptions only. Okay, sir. Overall, nice session, sir. Thank you.
Thank you so much, sir. So, Nilima ma'am, I think you got the answer. E91 is there. There are two more.
Yes, sir. Yes, sir.
Forgot the complete names, but there are four. As of now, there are four different types of protocols available.
Thank you, sir. Thank you, sir.
Asha, madam.
Yeah. Thank you so much, sir, for the engaging and insightful session. Thanks for walking us through the fundamentals of encryption. Yeah, fundamentals of encryption.
Any other questions, no?
Hello, am I audible, sir?
Audible.
Yeah.
So thank you. AI is speaking.
So thank you so much for the engaging and insightful session, sir. The fundamentals of encryption, AES, the glimpse of RSA, the way you have beautifully connected to the impact of quantum computing and all the approaches of quantum key distributions were excellent. Your explanation on BBA84 protocol, the process of QKD, and even the coding example that you have clearly explained gave us a lot of insights. Of course, we need some time to practice, but within the given time, I think you have covered the major concepts. So hopefully, we will connect sometime later for more engaging session. So we truly appreciate the way you have tied
Thank you. Thank
together
you.
all the classic. What we know so far was only classic, cryptography. But you have clearly tied together the classical cryptography with the promising quantum security. On behalf of all the participants, we once again thank you so much for sharing your expertise with us, sir. Thank you so much, sir.
Vishnu sir, thank you so much, sir, for your total presentation.